Hey folks. Okay, this time I want to get into looking at representing kind of more complex data types using our lists. So if you've got a tree that you want to represent, or a graph, or a stack, or a whatever it might be, and our kind of core compound data type is a list, how do we go about representing it? First off, this is where the dynamic data types come in really handy, because our list elements can be anything. So if you want to think about a particular data type, let's say I want to have a student record, or I want to have a stack, or I want to have a graph, I think about, well, what would one node in the graph look like, or what would one student record look like? And I think about, well, it's got, this field and this field and this field. So if we just think about those as the elements in the list to represent that, then we can get away with this, and we'll start writing functions that can go through and make sure that it's actually got the right structure, and when we create an element, it creates it with the right structure. So this is the idea that we're going to pursue. So we'll just work through a few examples today and see if we can get the hang of it. All right, again, as long as we can choose an appropriate structure and tailor our functions to work on that, we can represent pretty much anything we like. Now, the code for working with our data type is usually going to be pretty reasonable, readable, elegant. But if you start looking at the actual raw data for your graph or for your list or whatever, it's not going to be terribly human friendly, right? So this is going to work well from a coding perspective, but you're really probably not going to want to go through and start trying to draw up your examples by hand too often, once you get past the basic testing. So we'll start off nice and easy. Stack is a perfect place to start. Let's say we want to represent a simple stack where we can create an empty stack, we can push elements, we can pop elements off, we can look at the top element, we can check and see if the stack is empty, maybe we can check and see if something is a valid stack, maybe we can look up the size of a stack. So just a handful of basic operations. Now, we've got our list as a data type to use under the hood, and we've got the cons, car, and cutter operations available to us to work on the list, and that's pretty much all we're going to need. Maybe it'll be handy to pull a couple others out, but if you think about a push, we want to stick a new element on the front or on the top of the stack, and the cons puts a new element on the front of a list. So maybe we think about the front of the list as the top of the stack, and then the rest of the elements are underneath. So then something like car could be used to look at the top element, and something like cutter could be used to sort of do a pop to get rid of the top element. So that's the kind of idea that we can take as our just very basic implementation. So again, if we were to think about a stack that was supposed to be 11 on top, 3 underneath, and 10 at the bottom, then as a list it would look like just the list 11, 3, 10. Right? Top element is at the front, bottom element is at the back. So if we want to come up with an implementation, actually I threw an optional parameter in here that's just going to confuse things until we look at those next week. So why don't we actually go do this in code? All right, let's see. So what I'm going to do is look at just a handful of basic operations to go through and play with our stack. So we'll have a function that just creates an empty stack. So all this is really going to do, so we'll call this one stack, and all it's going to do is return an empty list. So that one's nice and straightforward. To see if something is a valid stack, so let's create a stack p function, all we'll do is say, well, is it a list? Right? We'll say our stacks can have any kind of data in them, so it can essentially be any valid list. So our stack p behind the scenes, we'll just see if S is a list p. Maybe we have a function to test true or false, is the stack empty? So at this point, let's start throwing in a little bit of error checking. So let's say if somebody passes us something, first we'll check and see if it's actually a valid stack, and then we'll see if it's an empty one. So the first thing we'll do is say, okay, if it is a stack, then all we have to do is see if it's an empty list, right? So we can just run null. And if it's not a stack, then let's give them something different. Let's give them like an error symbol. Say, okay, you gave me something that wasn't even a stack, never mind an empty or not empty one. And then we'll follow the same idea with a lot of the rest of these. If they pass us something and want us to do something with it as a stack, if the thing isn't a stack, then we'll just return the error symbol. So, getting the size of a stack. Again, we'll check and see if it is actually a stack. And if it is, then all we have to do is check what the length is, right? So we'll just use the list length function. Or I guess that's actually the sequence list length function. If we want to do a push, we said that would be a cons. I'm using spush as the name of my function here, just because there is already a built-in push, so just to avoid conflicts there. So, if they want to push a new element onto a stack, so they give us a stack and they give us an element, then again, we'll just make sure it is a stack. You know, if it's not a stack, we'll return error. If it is a stack, then all we have to do is cons that element on the front and return the new stack. So we're not actually modifying the stack they gave us. We're returning the new updated stack, if you like. Similarly with top, right? We'll check and see if it is a stack. And if we want to look up the top thing on the stack, we better make sure it's not empty. So here we've actually got a compound expression where we're saying, okay, if it is a stack and it's not empty, actually I guess I could have used a call to our empty function there, but that wouldn't have been a bad idea. So if it's a non-empty stack, then we'll return the top element. Otherwise, we'll return an error, right? So that error could crop up if they gave us an empty stack or if they gave us something that wasn't a stack. And then lastly, we'll do a pop. So pop is actually going to remove the top element and return the updated version of the stack. So again, for pop, it's got to be non-empty. So we'll make sure it is a stack and it's not empty. And if those are both okay, then we'll just return the cutter of the list, right? Everything but the top element. And if it's empty or if it's not a stack, we'll return error. So we can come up with a nice basic collection of stack routines. So let's try actually running that in the interpreter. So let's do a load of our stack.cl and let's create a new variable, my stack, and we'll call that stack function to go through and create it. Okay, so we've got this thing. And if you ever want to take a look at the actual underlying implementation, again, we can just see what my stack is. It's just a nil, just an empty list. So then maybe we try, let's do a, how about let's update my stack with the result of doing a push of my stack, and I don't know, 27. So try pushing 27 on the stack, and we get this new stack that's got a 27 in it. Hey! And if we try that again, so let's push, I don't know, how about foo this time? Right. So our push seems to be working okay. Let's take a look at what top gives us. So if we look at the top of my stack, just to see what that is, it gives us foo. Hey, so top seems to be working okay. So maybe we'll try, how about a pop? Right, so we'll try popping an element off and see what my stack turns into. Hey, it got rid of the foo for us. So again, we've got something fairly basic here. We can check and see if my stack is actually a stack. And it says yes, yay. Well, let's just throw something else at it. Let's see if stack P actually says, I don't know, 275 is a stack. No, it says it's not. Okay, cool. Alrighty, so we can come up with a fairly basic data structure where we've decided what the underlying representation is going to be, and we just make sure that we write our code to match that representation. All right, so let's start looking at maybe some other data types. So let's say we want to represent essentially what would be a struct in something like C, where we decide, okay, I want to represent a student record. So for a student record, it's going to have the student's name, their student number, and their email address in it. So again, we decide what kind of a representation do I want to use. So maybe I say, well, I've got 3 fields in my student record, so I'll just have a 3-element list. So when I create a student record, I will expect it to be given a name, a student number, and an email address, and I'll build a list of those 3 elements. If I want to check and see if something is a valid student record, then I'll check and see if it is a list with 3 elements, and the first one looks like a name, and the second one looks like a student number, and the third one looks like an email address. All right, if I want to update one of the fields, if I want to change the name or something like that, then I'll check and make sure that the thing I've been given, the new name I've been given looks like a valid name, and the student record I've been given looks like a valid student record, and then I'll change the name field. Right, so we can go through and start coming up with a reasonable representation. So let's go back and take a look at that in code again. What did I call this one? srec. So here we've got a function to go through and create a new student record. So it's going to return a list that's got a name, a student number, and an email address in it. Now, I'm not going to get too terribly fancy about checking that the name, student number, and email look particularly right. What I'm going to do is say, well, you give me, 3 values. I'll make sure that the first one's a string and treat any string as a valid name. The second one, I'll say, oh yeah, sure, any integer is a valid student number. And then for the third one, I'll just say, okay, well, any string for the email address. So we aren't getting too deep and meaningful about this, but you get the idea. So if they gave us something that doesn't look like a valid name, we'll return error. If they gave us something that doesn't look like a valid student number, we'll return error. And if they gave us something that doesn't look like a valid email address, we'll return an error. Otherwise, we'll build a list out of those 3 things. Right? So we'll create a list that's got the name, the student number, and the email address in it, and return it. So setting one up is reasonably straightforward. If I want to check if something's a valid student record, so let's create a student recp function. You pass me one thing, and I'll tell you yes or no, does it look like a valid student record? And I'll use the same sort of idea. If it's not a list, I'll say no. If it's got the wrong length, right, it's got to have exactly 3 fields for it to be a student record. So if it's got the wrong length, I'll say no. If the first thing isn't a string, I'll say no. If the second thing isn't an integer, I'll say no. If the third thing isn't a string, I'll say no. And if all those are okay, then I'll say, yeah, looks like a valid student record to me. If I wanted to create a method to change, or a function to change one of the fields, so let's create a change name function. You give me a student record and a name, and I'll update the name in that student record. So, same idea. First we'll check and see if it looks like a valid student record, and if not, we'll return error. Then we'll check and see if it looks like a valid name, and if not, we'll return error. And if both of those are okay, then we'll say, all right, well, let's set the first field in that list to the new name you've given me. Right? So we'll set the element 0 of essentially this list S to the new name. Right? So it should work out reasonably well. And so I've set this one up as a script, I think. Yeah, I set this one up as a script, and so we'll just throw a couple of sample calls in here. So we'll create a variable where we'll initialize a student record with the name Fred, the student number 123, and the email address fred@kmail. And then we'll just print it out. So we'll see if it actually created one the way we like. We'll try a call to student recp to see if it says that this thing is actually a valid student record. We'll try changing the name, and we'll print it out again just to see if this stuff works. So let's try running that and see if this actually seems reasonable. And it goes through, it prints out our student record, which looks about right. It says that that's an okay student record, yay. And it tries the name change, and that works out okay. So again, as long as we design an implementation that we like, and we come up with functions to support that implementation, we should be okay. All right. So let's plow happily on. we'll do one more here. So now let's suppose we want to represent a tree. And this is the one where it's going to start getting ugly, where the actual underlying data is going to get ugly to read as a human. So let's say we want to represent binary trees, where every node has got essentially a data field, a left subtree, and a right subtree. So again, our trees are going to be 3-element lists, right? The data, a left subtree, and a right subtree. So these left and right subtrees are also going to be lists that are supposed to be valid trees. So an empty tree is just the empty list. So if we've got like a 1-node tree, it's going to have the data value and 2 empty lists, right, as its content. Right? So if we have a tree with 1 in the root and no subtrees, it would just be 1 and then 2 nils. If we had a tree that had 10 in the root, 5 in the left subtree, and nothing on the right, again, we'd have that 10 for the data value, and then the left subtree would have its data value and it's got no children. And then the right subtree is empty. Right? So you've got this basic structure where you've always got a 3-element list, but some of those elements are going to be trees of themselves. So lists themselves. And so if we start looking at a few examples again, if we've got this tree that's W with children X and Y, again, we've got W and X. The X node has got no children, and the Y node has got, or if you like, empty children. Or if we wanted to start getting a little fancier and we say, okay, let's say we've got X on one side and Y on the other side has got a right child, then we've got X with its 2 empty children. We've got Y that doesn't have a left child, but it's got its right child, Z, which has no children. And so you can see that it's starting to get a little less intuitive to read if you're going through and just eyeballing this. Again, a program's not going to have any problem going through and processing this because it's just looking at, is this thing a 3-element list? Do something with the left subtree or the right subtree. And again, if we start getting this deeper and deeper, if we want a tree with sort of the 3 layers and 7 nodes, then the data structure is going to wind up looking something like this. Right? We've got A, and it's got a left child, and it's got a right child, and that left child has got its 2 children, right? A left child and a right child. So it does actually make sense if you sit down and read it through, right? The second one's got a left child and a right child. But again, if you're just trying to eyeball this and get all your brackets right, especially if the tree's not balanced, it does get kind of ugly to try and read. But the structure is pretty straightforward. So if we wanted to start creating methods, again, let's say I want to create a new tree that's essentially just got 1 data value in it. So I guess we could also just we could have a function to create a new empty tree that just returned an empty list. But here, let's try one where we're going to create our tree, we're going to initialize it with 1 single data value. So you give me the data value. And essentially, I'm creating a list of 3 elements, right? The data value and 2 empty subtrees. If I want a function that's, you give me a tree and I'll get the left subtree, then I might want to go through and say, okay, well, I want to make sure that the thing you gave me is actually a tree. So presumably we go off and write a tree p function that checks if something's a valid tree. So if the thing you gave me is a valid tree, I'm using tr here just because t is the constant for true. So if the thing you gave me is a valid tree and it's not an empty tree, then the left subtree is that second element. So I could either return nth or I could return the head of the tail of the tree. So, right, the tail of the tree would give me the 2 subtrees, and the head of that would be the left subtree. So whichever way you want to go, you can either return the head of the tail or just, nth one, and you should be pretty good. If I wanted to go through and have a function that changed the left subtree of a tree, again, we'd do something like say, okay, well, make sure that you gave me a valid tree in the first place, and make sure the thing that I'm supposed to be substituting as the left subtree is actually a valid tree. And make sure that the left, or this is inserting it, sorry, as the left subtree. Make sure that there isn't already a left subtree. If all those things are okay, then I'm going to set either the nth one of my tree to L, or set the head of the tail of the tree to L. So again, we can go through and build just simple functions that, do the error checking and then set the new tree content appropriately, or get the new tree content appropriately. So if I wanted to, we mentioned this idea of having a tree p function to see if something is a valid tree. Well, if it's not a list, it's not a tree. So that part's easy. If it's an empty list, that's okay. So if it's an empty list, we'll return true. Right? It's an empty tree. If the length of the list isn't 3, it's not valid. Right? We've already dealt with the empty trees, so we know it's not going to be a 0 when we get here. So if it's the wrong length, it's not a tree. We'll return false. And then we'll do a recursive call on the two subtrees. If the left subtree isn't a tree, we'll return false. If the right subtree isn't a tree, we'll return false. And otherwise, we'll say, well, it seems to look, it's got the valid structure as far as we're concerned, so we'll go through and return true. So we can come up with a method to check the validity of a data structure. Now, if I wanted to do an in-order traversal to print the contents of a tree, same sort of thing. We'll check and make sure it's actually a tree. So if it's not a tree, we'll print some kind of an error message. If it's an empty tree, we just won't print anything. We'll just return true, for instance. And otherwise, what we'll do is I want to run 3 instructions. I want to print the left subtree, I want to print the data in the current node, and then I want to print the right subtrees, right? So our in-order traversal. We'll take a sneak peek at the use of blocks here. So I can put multiple instructions in a single statement with the block function. So I say block, and I throw in a symbol just as the name for my block. And this is actually used for jumping between blocks and things later. But for now, treat it as I use the block function, I give it a symbol as a name, and then I just have the set of instructions that I want to run. So I want to run print tree, and then a print, a format, and then another print tree. So again, we can go through and build up fairly complex data structures. It's just a matter of picking a representation and writing our functions to match that representation. All right, that seems like a good place to leave it for now.